Good morning. Welcome everybody to this week's GR seminar. This week we're actually very glad to have Liam from University of Vienna, and he's going to talk about this new work and very exciting work on the past maximal development of near-FLRW data for the Einstein scalar-field Vlasov system. So Liam, welcome, and please take it away.
Hi there. Thanks again for the invite, and good evening from our end, I guess. So this talk's going to be about the combination of both preprint stuff published on the archive in the last year, the first one together with my supervisor, David Fajman. Both of those mainly concern past stability of Big Bang formation in presence of Vlasov, but then also the scalar field in there to get stability. There's also a bit of an extra thing regarding stability in symmetry in vacuum that's in the second paper. Depending on time, I'll get to that right at the end as well. But since the core of these things is very similar, just in different spatial dimensions with different proofs, I decided to just combine both of these into one. Cool. Then let's just get started a bit with the overview. One sec. There you go. So general motivation here is that we look at this from the strong cosmically sensitive conjecture perspective. Generally, we would like relativity to be deterministic. So if we have initial data and evolve it, we don't want, when the maximal development breaks down, that the reason for that to be there's different extensions that you could have, because then relativity wouldn't be deterministic anymore. So we want there to be some breakdowns that this is inextendable. In cosmological contexts, what we usually look at here to specify the type of inextendability is inextendability, got the crash notification again, inextendability in the C2 sense. So that we look at this particular scalar here, the Kretschmann scalar, this particular curvature invariant, and that when we evolve, that wherever our maximal development becomes incomplete or quasi-geodesically incomplete to be specific, that this particular curvature scalar blows up. And when that blows up, that also means clearly that we can't extend the spacetime in any C2 fashion. The reason we look at this, we'll see in a second that just the model spacetimes that you would usually consider here are precisely ones that have this type of curvature blow up towards the past. And there's also the way you'll quantify Big Bang formation. But on top of that, it's also been shown by work with some of the links to them a couple of years back, that even just assuming the like some reasonable assumptions in terms of spatial homogeneity of your spatial manifold, that in those circumstances, you're going to have in precisely this quantity blowing up. And otherwise, also, it is the curvature quantity that is scalar and coordinate invariant that contains the most curvature components. So it's a reasonable thing to look at to measure how we break down in the C2 sense in the Einstein equations. So the usual model spacetimes in vacuum are the Castor spacetimes. We would like the cosmological models to be ideally both spatially homogeneous and isotropic, so the same in every point and the same in every direction. In vacuum, just assuming spatial homogeneity leads you, again, with some other assumptions, to the Castor spacetimes as your standard model if your spatial model is the torus. Castor spacetimes look as you see on the slide, where each coordinate direction is scaled by t to the power 2qi in the metric. And for that to be a solution to the vacuum equations, we have to satisfy the Castor constraints here in the bottom left. That the sum of the exponents and the exponents squared is 1. In vacuum, we can't have isotropy because of these relations, but at least we have spatial homogeneity. So these are the standard vacuum solutions you look at to model cosmology in the vacuum sense. These solutions have a Kretschmann scale that's proportional to t to the minus 4, depending on these Castor exponents, even in general dimensions. I just put the three-dimensional one here. And as a result, what we then call the Big Bang is this blurb of the Kretschmann scalar towards the past. The question is now, of course, is this something that holds more generally, be it in the vacuum equations or be it in other contexts? First, look at oops, that's the wrong button. The general conjecture that goes back to the 60s by Belinsky, Klapanov, and Lifshitz is that this picture, the behavior of Castor spacetimes, describes in some sense the generic behavior of at least vacuum solutions and even more general solutions. Long story short, the idea here is that towards the past, your evolution is asymptotically velocity term dominated. So this idea that every point is the same holds in the sense that we can kind of ignore spatial derivative terms in the evolution. And thus, we are looking somewhat similar to the behavior of just the evolution of the homogeneous solution. However, these homogeneous solutions in a dynamical picture generally aren't stable. And what you have generically in vacuum is that you oscillate between different Castor states, and this becomes very, very chaotic towards the past. In the original papers, it's then also conjectured that this, as then later got phrased by, I think, Wheeler, that matter does not matter. So that if we couple most matter models into this, that these vacuum oscillations are going to dominate whatever matter content there is in there towards the past, and this is going to be the thing that mainly dominates past behavior. Even in those papers, there are some caveats, but the one reason that I think this is pushed forward the most is that this in particular is what you see also in a dynamical picture for radiation, which is the matter model that you expect to be dominant towards the past. If we then go back to this idea of cosmic censorship, this is a bit unfortunate to us because it makes it very difficult for us to verify A, whether this Kretschmer scalar blows up towards the past for general solutions, and though we can say from Penrose theorems that it's probably going to happen. There is a singularity formation. If you want to quantify this and see whether we quantitatively behave like t to the -4 for general solutions, this is in general going to be difficult. One way around this is symmetry, and if I have time at the end, I'll briefly touch on symmetry. But the other way around, and is the one that's had a bit more work on it recently, is scalar fields. Scalar fields are a matter model that are able to segment on this and give you basically an additional degree of freedom to be able to create stable or quiescent Big Bang formation. Quick recap, the scalar field energy momentum tensor is given by that thing there. And this is just, for my context of this talk, the massless scalar field. You could also add potential probably for a lot of these results, even if it isn't explicitly stated. But yeah, that is what I'm considering here as the massless scalar field. What this leads to as the classic reference solutions are the generalized Kästner spacetimes. These look exactly the same as Kästner spacetimes, just that to satisfy the Einstein scalar field equations, you change the Kästner relations around and have what is in effect an extra Kästner exponent given by the time derivative of the scalar field. And the time derivative of the scalar field always behaves like a constant times t to the -1. Essentially, because of this is why you are then able to generate stability from this, just because you have the ability, because you just have the ability to, add small perturbations in here. In particular, having this extra degree of freedom is then also the thing that now allows you to consider isotropic solutions, and thus finally the ones we're going to mainly look at in this talk, which is FLRW spacetimes. So these are the spacetimes that are actually spatially homogeneous and isotropic. So for this talk, whenever I have an M here, it's always going to be a closed orientable in brackets, because that's more or less without loss of generality, closed d-dimensional manifold with constant sectional curvature. D is always going to be 2 or 3. Most things are going to hold for either of these cases, and then sometimes higher dimensional things, but then it's not the general curvature case usually. FLRW spacetimes are just taking this type of hypersurface and expanding that in time with a scale factor A. The scalar field model, again, is here in these reference solutions, the scalar field solution that is isotropic. So the time derivative, when you look at what comes out of the wave equation, is then proportional to a to the -d, and the spatial derivative vanishes. For this to be a solution to the Einstein equations, we have to satisfy the Fajman equation, which in general then looks like this. The exact form of this is not going to be too relevant. What is relevant, heuristically, is what happens when you solve this. One can show that you always hit 0 at some point. So we say at 0, which is where the Big Bang is placed. We say at t equals 0, that's where we put our Big Bang. And as we approach the Big Bang, if you solve this differential equation, the singular initial value problem, then the scalar field, the scale factor behaves like t to the power 1 over d as we approach the past. So a to the -d is just t to the -1 up to some errors. Again, in the flat cases, it's just up to a constant t to the -1, so basically just t to the -1, so a to the -d. In the case where we are not over the torus, so over a sphere or over a closed hyperbolic manifold, then you have this geometric term here that changes things a bit, but towards the Big Bang, it's dominated by this term from the scalar field that's in front. So that's why we basically have the same look towards the past. Now, in this model, this is where first nonlinear stability results were proven, and they roughly look like this. These are 3 results, one by Dotniansky and Speck in the toroidal case, then just by Jared Speck in the spherical case, and then by David Fajman and myself in the closed hyperbolic case. But in all 3 cases, the end result is essentially the same, again, because geometry is essentially dominating the asymptotic behavior by the strength of the scalar field. So to summarize, when you look at the maximal globally hyperbolic development of near-FLRW initial data to the scalar field system, Then, as you would expect, this becomes statistically incomplete towards the past, so t equals 0, where we place the Big Bang. And this is driven by not just Kretschmer scalar blur, but in fact by stable Kretschmer scalar blur. And in that sense, we have verified that the strong Coptic censorship conjecture holds for solutions that are nearby the FLRW solution with their nearby generic initial data without any symmetry. In particular, those solutions are then also asymptotically velocity term dominated. I picked out some variables in particular for the convergence. The second fundamental form as a 1-1 tensor converges to the trace tree part k hat bang, which will be important later, plus this part here next to it, which is just a trace. The rescaled unit normal of the scalar field that converges to its reference quantity in the FLW plus this psi bang quantity here, and the lapse entirely converges to 1. This k hat and psi bang, these are things that in the FLW solution are 0, and in this general solution, these are controlled by the perturbation size, so less or equal than epsilon up to a constant. With the metric, it's not quite as nice, at least in this formulation and the way it's stated in all of these papers. Here, I should state this in dimension d equals 3, all of these results, because it's space on dimension 4. Because we converge to something fixed towards the past, that means if we just time integrate the evolution equation for the metric, we're going to have to deal with the fact that this is essentially an exponential ODE in terms of the metric components. What that means is that it's not the metric itself on the spatial hypersurface that converges, but it's the metric renormalized times this slightly ugly exponential factor here just comes from the fact that we know what the second fundamental form is and thus can integrate the evolution equation directly. But this renormalized thing, that converges to a quantity on the Big Bang hypersurface, and that quantity is roughly up to a small error, again, just the reference metric, so the constant curvature metric. M bang is not a metric, I should stress, but it is a tensor that is in its components close to the metric with uniform estimates. And finally, we can take the asymptotic Hamiltonian constraint, which constrains how psi bang and k hat bang behave towards one another. So far so good. Since then, in just looking at the scalar field system and also nonlinear scalar field system, this has been extended even beyond just the FLW picture. Work by Florian Bayer and Todd Oledick, as you would expect from the BKL conjecture, which also says all these oscillations are local, has shown that you can localize this entire procedure for the torus in spatial dimension largely equal than 2. So if you pose local initial data that's close to FLW, yes, then that controls a local region in which you have a Big Bang and the Big Bang is stable. This is then also extended to generalized Kassa solutions that aren't too anisotropic, which is called subcritical in that paper. For the case of d equals 3, this is just saying all Kassa exponents are positive, which is precisely the requirement that you would need where you can't even expect stability to hold. And then there's also an additional thing in this Fondatel-Fontansky spec paper, which I might get to later. And then that has been, in particular, has been further extended to go even away from stability. Work from 2 years ago by Hans-Udo Grünier, Pearson, and Dingström, that's shown that if you take just general initial data to the scalar field Einstein scalar field equations, where the second fundamental form and the scalar field are strong enough compared to the other parts, and you're close enough to where the Big Bang would lie, then you also have this type of stable Big Bang formation in the sense that this all asymptotes towards a velocity term dominated picture where the Kretschmer scalar blows up stably at these orders. Essentially what's done there is that instead of perturbing near a Kastner solution, a particular one, you construct what you expect the solution to be, or roughly to be, called the scaffold, and then show that you stay close to the scaffold. So, are there any questions on this overview on the scalar field equation so far? Cool. So long story short, we now have a pretty good understanding as to how good scalar fields are in being able to stabilize the Big Bang, and that gives us a good playing ground to work with. The thing from a physical perspective, though, is while a lot of cosmologists use scalar fields precisely to get, especially nonlinear scalar fields, get the type of evolution, especially in the early universe, that you would like, for example, to generate inflation, we, of course, expect there to be other matter models in the universe, and we want to see whether the strength of the scalar field works when we extend it to the other matter types that we expect to at least exist in the early universe, if not dominated. And the first candidate for that would be a perfect fluid solution, because that is usually what you use to model cosmology and usually use for these FLRW models in particular. That work was done, I'll get to that in a second, by Florian Bayant and Olenek again. And what they looked at was the Einstein-Euler scalar field system, again, scalar field, just a linear one, same as before. And then additionally, coupled that to the standard Euler equations, we have to specify an equation of state. And the one they specify is the simplest one, where we just have linear dependency between the pressure and the density. And this linear factor is given by the speed of sound squared. In the work, they then looked at the spatially flat FLW solutions, so over the torus. And what it showed is that if you couple that to isotopic matter, then these FLW solutions are stable towards the past, and you have very similar results for the Kretschmann scalar and everything involved, as long as the speed of sound squared is greater than this threshold 1/d. In particular, the near-FLW solutions, they approach, again, in the scalar field sense, they approach a generalized Cassar solution, and the fluid asymptotes towards the fluid at rest, which is what you are perturbing it around, is the FLW solutions. The FLW reference solutions essentially at first order look like a generalized, like a scalar field solution that is FLW, and then there's some lower order corrections that come about from there being a fluid at rest that's coupled in, and then you have to change the Friedmann equations around a bit. But essentially, it is almost the reference solution is having a scalar field FLW spacetime plus a fluid at rest. And then when you perturb that, what they showed is that as long as you're above this threshold, not only do you asymptote towards at leading order the same background as you would have if the fluid weren't there in the first place, but then the fluid perturbations also stabilize and you just converge towards the at rest solution, the isotropic one, towards the past. Now, the one thing that's a bit unfortunate about this, but it is slightly to be expected, as I'll get to in a second, is that this threshold is precisely the one that you would want physically. This threshold, especially in dimension 3, this is 1/3, so this is the equation of state of radiation, but this is in general the equation of state of radiation. And radiation is the thing that physicists expect to be dominant, the dominant matter model towards the past, which is why you would particularly like to know things about that. The thing is, though, even if you just look at homogeneous solutions on fixed Kastner backgrounds for the Einstein-Euler, on fixed vacuum Kastner backgrounds, even then, I phrase this a bit for you here in the text, but homogeneous solutions, as soon as you go below this critical threshold, start to tilt, and then they aren't asymptotically null and asymptotically at rest anymore, but asymptotically null, completely changing the structure essentially. This is something you observe there, and precisely at this threshold, you have the homogeneous solutions are constant, have constant fluid velocity components. So there is going to be some change that they have to expect. In this work for them by Philippe Leflore, they are able to look at Einstein-Euler in Gaudi symmetry and how you can evolve from the Big Bang singularity outwards. And they're able to do this as long as you're above this threshold. At the threshold, they're able to do this under some additional assumptions on some polarization of the spacetime. And below this threshold, they see the system is not going to work because the Fuchsian approach that is underlying this for the Euler equations just breaks down. And this breakdown is actually also what is explicitly seen if you look at this Bayer-Olenek paper on Einstein-Euler scalar field stability. There, you also just need a certain sign in the evolution of the fluid velocity. Precisely at the threshold, you lose this term with a strict sign, and at that moment, you just have to deal with geometric oscillations. And once that sign flips, then everything tilts, and you can't expect stability anymore. Very recently, Florian Bayard, Olenek, and the PhD student of theirs, Elliot Marshall, then looked at this numerically, what happens below this threshold at the Einstein-Euler scalar field system in Gaudi symmetry. And below this threshold, you have precisely this tilt that you see with the homogeneous solutions as well. So in a sense, in all of these cases, you are dominated by the homogeneous solution. It's just that means below the threshold that you don't have stability because you're going to have blow up of the gradient towards the past, and that's going to break things. You might be able to control this in some way if you are able to see of this tilt instability. I'm not saying it's impossible, but at least the picture is going to change a lot once you do this. However, at the threshold, even that numerical analysis and also the proof, if you look at the comments there, is inconclusive. The numerics there are inconclusive simply because the closer you get to the threshold from below, so from the supercritical region up to the critical one, the longer it takes for the singularity in the fluid to materialize. And as a result, the less at the threshold, it might just be that while they don't observe this instability occurring, this might just be that the simulations don't run long enough. That's roughly what they say in the paper. So there's hope that you might be able to save this. And similarly, from a rigorous perspective, when this one term with a positive sign or with a good sign cancels, you might still be able to control geometric behaviors in the Einstein-Euler scalar field system, maybe with some additional assumptions in symmetry, like in the Vlasov paper, or maybe there's some hidden structure in there that maybe one can use to some extent. So what do we do? And the title gives it away, so it's always a bit weird to me to pretend that it's a surprise. But the idea to broach this, at least to an extent, is to look at Vlasov matter instead. That was the wrong thing. Vlasov matter. Quick recap. Vlasov matter usually models the behavior of a gas. The gas is given by this distribution function, which I'm going to denote by f bar, for reasons that will be a bit clearer later. The associated energy momentum tensor is then given by this quantity over here. All these particles have a fixed mass m. I'll be looking at just the cases where that will have mass 1 in the massive case, or the massless case where there's mass 0. The fact that they have this mass means that the particles essentially live on this mass shell here, which is a tangent space over the spacetime. Because these are particles, they are preserved by geodesics, and thus the distribution function as a whole is preserved by a geodesic spray, which is then referred to as the Vlasov equation. So first, why is this a reasonable model at all for the cosmological perspective? This is a bit more relevant towards the future. If you look at the universe right now, one can, and sometimes does in kinetic models, look at each individual galaxy cluster that is spread out as a smoothed out point particle, where collisions are very unlikely just because they are spread out far apart and will spread out even further. As for this type of collisionless gas, you would then model this by the Vlasov equation, and this gives you a reasonable model, at least in a massive case. Towards the past is, of course, going to be a bit dodgy from a heuristic perspective, because towards the past, when the universe contracts, we're going to expect collisions to be very relevant. But at least there's a good first approximation from a physical perspective to what one would expect if we want to model the universe as a gas instead of as a fluid, plus a scalar field being around as well. But also from a mathematical perspective, it just looks like radiation towards the path, which is what we want to do. If we look at the density from the energy momentum tensor and the pressure, just written down here the formulas for the sake of completeness, then in the massless case, this is for isotropic solutions just exactly radiation, the equation of state that you get out. In the massive case, asymptotically for isotropic solutions is asymptotically then still radiation, because the matter part is dominated by the momentum part in this P0 component towards the past. In particular, in the massive case, because this looks like dust towards the future, as a gas with massive particles should, this actually interpolates smoothly and cleanly between these two dominant matter models that we expect there to be in the past towards the Big Bang, and the future, in the past radiation and the future dust. So from that perspective, it's a convenient way to kind of maybe ideally even couple both scenarios at once. I'm not going to do that for this talk, but that is something you can probably do with this going beyond. So just looking at the Vlasov equation first, there have been a lot of results. A lot of these results, because you have to, because radiation itself is unstable, have to be restricted to symmetry to be able to control this well towards the past. The first results, and there's a lot of these, are results for Bianchi spacetimes. I think almost all Bianchi classes are covered in various different papers. I've listed some of the authors here. What unifies all of these? There are different constraints in the different spatially, locally homogeneous spacetimes that you can have. But in all of those, you generically have an isotropic singularity, and if oscillations are possible, you would usually also see oscillations, as you would then expect from a BKL conjecture again. There is, of course, always an isotropic solution in there, because as soon as you have matter, you can generally construct this, but it is always the least favored option in the dynamical solution space, vaguely, or at least it is very unfavored compared to these more general isotropic cases or oscillations. In surface symmetry, there's a good, but very important work by Lane, which looked at the perturbations around the vacuum solution with Kastner exponents given then by 2/3, 2/3, minus 1/3. And then surface spherical and hyperbolic symmetry. In all of those, if you look at perturbations, then this converges back towards these Kastner exponents. This was then also extended to more general things you converge to for the full Einstein scalar field Vlasov system by Tian, Kong, and Rendell. I say partial extension here in the slides because there is a part in their proof where there is the behavior of the momentum support for the Vlasov distribution is not proven, and they leave this open. And as far as I'm aware, this hasn't been fully filled. But at least what this does as a proof of concept is that there is a way to extend this idea of stability around the vacuum solutions to stability around Einstein scalar field solutions once perturbed within the Einstein scalar field Vlasov system. From the perspective of cosmic censorship, there is also something a bit more general approach by the Fajman and Rendell. Again, spread out over the various papers. I think some of those just by Michalis. Again, looking at spherical surface or hyperbolic symmetry with various cosmological constants. What they do there, instead of looking at this more general stability picture where you try to control all solution variables, is that they use this transport structure of the Vlasov equation to transport curvature components and show C2 extendability that way. This is in some ways more efficient because you don't have to rely on these types of stability ideas of perturbing the explicit things, but then also means that this isn't as quantitative an estimate by comparison, which we would just like to have to be able to exactly describe what happens towards the past. All right, that then leads us to the setup for our results. So let's quickly recap. We look at the Einstein scalar field Vlasov system. So we have these Einstein equations coupled with the linear scalar field equation and the Vlasov equation. Our reference solutions that we perturb around are the FLRW solutions. Again, the spacetime metric and the scalar field are precisely just for the Einstein scalar field solutions. It is the isotropic solutions on these manifolds. Well, for the scalar field distribution on this manifold and the FLRW metric. And we also take the isotropic solution for the Vlasov distribution. In these natural canonical momentum variables, where this is just the coordinates induced on tangent space by some arbitrary choice of coordinates here in space, then this is just given by something which depends only on the absolute value of the momentum, depends on the spatial metric, times the scale factor that I then just need to have to be a solution on the FLRW background. For the sake of convenience, we will rescale our momentum variables by a factor a squared. If you don't like this rescaling, you can also just think of this as p index lowered, which I guess some people would argue will be more canonical. For our purposes, it will just be a bit more convenient to look at this as a rescaled variable rather than having this in the lower indices. But you could also do that if you'd like. In that case, then our particle distribution is just some distribution that depends only on this rescaled, on the absolute value of this rescaled momentum. Of course, to be a particle distribution, we require this to be non-negative. And additionally, we also require this F maximal to have compact support. So that's basically just that the energy momentum tensor is always well defined. One could maybe, with a lot of work, extend this to more general things where you just have sufficient decay towards infinity. But momentum support being compact is going to be the thing that's easiest for us. Additionally, in the massless case, we also have to assume that the zero isn't in the support of F maximal. So on the other hand, going back to this, that there is in the mass shell, our momentum support is strictly bounded away from the zero section. Again, this is just to, in the massless case, ensure that everything's well defined, the energy momentum tensor. Maybe one can extend this again to more like strict decay rates or like behavior rates towards this zero section, but we restrict ourselves to the compact case for here, and also because a lot of local resistance results only work, or at least are only proven, with compact momentum support and momentum support bounded away from the origin. For this to be, again, a solution to the anti-scalar field system, we have to satisfy the Friedmann equation. Again, you can essentially treat this heuristically as if the Vlasov matter weren't there at all. Because asymptotically, as you can see, this here is always going to be stronger than this here. It's both spatial dimension 2 and 3, where this here is the rescaled Vlasov. Where this here is the rescaled Vlasov density. So again, to recap towards the past, that means that the scale factor A behaves like t to the power 1 over d. Wonderful. This already gives you essentially heuristic as to how the first of this result is going to look, because the Friedmann equation is dominated by a scalar field. Neither the spatial geometry nor the Vlasov matter matters too much in the asymptotics at leading order. And so the first part looks very similar, will look in a second very similar to what you have just in presence of the scalar field. So what do we have? So again, we take some near-FLRW initial data in spatial dimension 2 or 3 to the Einstein scalar-field Vlasov system. Additionally, our Vlasov distribution initially is again non-negative and again has compact momentum support. And again, in the masses case, has this momentum support bounded away from 0. So that everything's well defined for this distribution as well. We also assume CMC per se. I'll mention that again in a second. This is without also generality though, because we are perturbing near CMC and this can always arrange this. So first off, again, if we look at the past development of this, it becomes causally geodesically incomplete towards the past. And at that past threshold, the Kretschmer scalar has stable blow-up of order t to the -4. And the spacetime variables and the scalar-field variables are again asymptotically velocity term dominated with the same asymptotics as we had if the Vlasov matter weren't there at leading order. And similarly, again, all the footprint variables that are listed here are controlled by the perturbation size and the same way as before, and the Hamiltonian constraint also holds asymptotically. So from this end, this is just what you would expect, that Vlasov matter doesn't matter too much. There is now, of course, nuance of what actually happens with this critical matter model towards the past. And that's a bit difficult to phrase. So first off, just what do we have as rough estimates on this? As rough estimates, if we compare this renormalized Vlasov distribution to its FLRW counterpart, we don't quite converge. We converge up to some scale factor, some small negative power of t. And then similarly, if we then translate this over, this behavior means that any part of the energy momentum tensor, so in particular, for example, the density, is going to satisfy very similar bounds on both also a Sobolev level, which are dropped here, but then also just on a C level at suitable order, that is going to be small up to a small order offset. So we can't fully control the components of the energy momentum tensor in terms of what gets plugged out physically, but we can almost control the leading order up to a slight offset. But what happens in a bit more in particularly, and I'll fill this with a bit more meaning as we go on. So we can look at this rescale quantity F asymptotic, which is given by this rescaling of the momentum variables here, dependent on this k hat band quantity. It's a quick reminder that k hat band quantity is this quantity here, which is what the rescaled trace-free part of the second fundamental form, so the rescaled shear, converges towards the past. Note that this exponential factor that we'll see again in a second is precisely this one down here. And that comes from the metric behavior. If we renormalize the momentum variables by this, and I've written this down again back on the canonical variables for the initial distribution, not this renormalized one, then this new expansion renormalized quantity, that actually then converges towards the past. In the paper in the spatially three-dimensional case, we phrased it a bit differently. There we subtracted something that looks very similar to this, and then there's some technical issues that mean that isn't quite as precise. In the two-dimensional paper, we've now phrased it like this, and we'll probably update it in the three-dimensional paper as well, because that also works independent of the spatial dimension. So this asymptotically renormalized Vlasov distribution converges towards a limiting thing that lives on the Big Bang hypersurface, and that limiting object is close to the initial distribution, up to some power of epsilon, so up to a power to perturbation size. But I mean, we can see here as well, at t equals t0 at our initial hypersurface there, this is then just the same as the original distribution, well, renormalized. But then as we go towards the past, this exponential factor here is going to behave fairly poorly, because this here, as I recall, behaves like t to the power -1. So this is some exponential of a logarithm times what is effectively a 1-1 matrix. A bit more explicitly, let's look at an example. This k hat quantity is always going to be trace-free, and it's always going to be small. So for the sake of heuristics, let's say it behaves like 2 epsilon minus epsilon minus epsilon as a diagonal thing. One can also show that this is self-adjoint, so this is also, we definitely have some eigenvalues, so we can write it down in a diagonal form with an appropriate frame. And let's say that we are lucky, and the limiting distribution that we get is not just close to the initial distribution, but it's exactly the FLRW distribution for some magical reason. In that case, if we then translate this renormalization back, what that means is that towards the past, at least, the Vlasov distribution with these V momentum variables behaves like a function of this inverse matrix exponential times V. This here just being my notation for a matrix product. Now, this here is basically minus log t up to then some t0 things that we ignore for the heuristics. So this is then going to be t to the minus 2 epsilon, t to the epsilon, t to the epsilon as a diagonal matrix times v. Now, as t goes towards 0, when we have a negative exponent, that's going to become very large. And because we have compact momentum support, that's going to definitely leave the momentum support. For the things where it's then scaled with t to the epsilon, that's then pulled towards the center. So if we have a non-zero value at the center, that means we measure this if we are orthogonal to this one direction, we have a positive eigenvalue, and 0 otherwise. In the massive case, if we in the initial distribution had the fact that this is strictly positive at the origin, then this is precisely limiting behavior. We approach the eigendirections of this limiting renormalized shear. In the massless case, it's even more awkward than that. In that case, because we also can't measure particles that are nearly at rest, that means that we still have this type of conjugation in these eigendirections, but the particles will also then asymptote towards having very, very large momentum the closer we get towards the past. What this means in more less mathematical terms and more just heuristic terms is the way the Vlasov distribution behaves and the way these particles that we measure, what momentum they have, is going to change a lot from point to point. Even the types of directions that can happen, the dimensionality of the space that we congregate towards is going to change from point to point, in the three-dimensional case at least, because that's going to be dependent on the signature of k hat bang, which can change locally because it is perturbed around 0. So what this tells us is that this is very critical. This is something that wants to be anisotropic, but because this anisotropy is all contained in the momentum variables, and essentially, if we go back, here it is. If we go back in the momentum variables, this ends up being almost integrated out. This doesn't actually affect the Einstein equation too much, and thus, in the Vlasov case, we can actually still have the stability result that is, at the very least, going to be more difficult as soon as we look at a full radiation fluid. All right. This is the point where we'll start talking about elements of the proof. So are there any questions on the results before I start going into some of that? Okay. Just checking the time. Okay, I'll see how much I can do within 15 minutes. Cool. So let's start just with the general overview. So again, as I mentioned before, we can assume that our initial data is constantly in curvature without loss of generality. This is an argument that's the same as in the scalar field settings, where because we are nearby, we can kickstart some local evolution in an appropriate gauge, and then using the Prism function theorem argument, we can find a nearby hypersurface to our initial one, where we are actually strictly CMC and not just near CMC. Because then due to Cauchy stability, we can then ensure that if we adapt our initial epsilon appropriately, that we then are still in a regime where we can prove stability. So essentially, we can just pretend our initial data was CMC from the start. The gauge we use for the evolution in all these results is CMC gauge with zero shift. The reason for this is that if the shift is there, for example, when I started out with the project, even before Vlasov, we tried to use CMC as H. The issue that you then run into is that because the metric behavior is very difficult to control, this type of control you can essentially only or best do after the fact once you know how the second fundamental form behaves. That translates over to the shift equation, and then the shift becomes difficult to control and breaks the energy estimates, at least as far as I looked at them. Being able to ignore the shift ignores this direct coupling of the metric into your energy estimates, which is the worst behaved variable out of the variables that you have to consider. So CMC gauge to zero shift is just the one that's largely used for a lot of these stability results, not universally, but largely. Then, of course, we need some continuation criterion. And one can prove that all we need to do to show that we can continue the solution is that some low order energies remain bounded. This is independent of regularity, and that the Vlasov momentum support is bounded, and the massless case also bounded away from the origin. So the setup of the argument is then a standard bootstrap argument. We assume that some collection of the solution variables have a control in the Sobolev norm and then also in the supremum norm that is small up to this constant diverging factor with a small power sigma times this constant c0. The reason we need to assume this is, again, that we don't know how the metric behaves a priori, so we need to account for the fact that there's going to be offsets in the metric, which we account for by this divergent factor. The goal is then to improve both this prefactor and this exponent to these slightly arbitrary different values. And then additionally, so that we can use a continuation criterion and then continue beyond the bootstrap interval, we then also assure that our momentum support remains bounded until we reach the Big Bang, and then similarly also bounded away from the origin in the massless case. Very quickly, just brief showing in the following. Large G is going to be the renormalized spatial metric. The sigma sharp is the renormalized shear as a 1-1 form. Large N is lapse -1. These are all just the renormalizations from what we expect from the FLRW picture. As I said before, VI is the rescalar momentum variable, and V0 is then defined analogously, and F is our renormalized Vlasov distribution. I realized I didn't put the scalar field in here. Psi is the renormalized spatial, the renormalized normal derivative of the scalar field. First, quickly, oops, again, wrong button, on the spacetime geometry. I'll going anti-chronologically here, and I'll start with the two-dimensional case, actually. In both cases, in 2 and 3 dimensions, in CMC gauge of zero shift, we can schematically write out the evolution equations, in particular of the shear as a 1-1 form, as listed here. Now, in the two-dimensional case, this Ritchie tensor over here is just pure trace, and sigma sharp is trace-free. So in the energy estimates, this just ends up not coupling together at all. So what is usually something that then structure ends up being a wave equation, on an energy level in CMC-TC gauge, you can essentially just treat it as an evolution equation coupled to an elliptic equation for the lapse. So in 2 spatial dimensions, a lot of these estimates simplify very quickly, and you can get good estimates on the shear that you can grunwall and then use to get control on your quiescent system. In 3 spatial dimensions, this is of course a bit more complicated because you can have more general things for the Ritchie curvature. The idea here is, though, basically just one can view as just extending this idea upwards, even though that is not the way that we looked at it, which is looking at, wrong button again, Bell-Robertson variables. The Ritchie tensor, the spatial one, might not be pure trace anymore, but we can measure what the trace-free component is by looking at the Weyl components of the spacetime metric, which then decompose and are fully given by these 2 Bell-Robertson variables, E and B. The Ritchie tensor is then just, once you look at the Gauss-Gratzky constraints, and this reduces to the Hamiltonian constraint if you take the trace of this, the Gauss-Gratzky constraints give you that the E component is just the Ritchie tensor up to some things dependent on the shear and some zero-order matter terms. And in particular, E is trace-free. So instead of having something which is pure trace, we now have something which is the trace-free part in 3 spatial dimensions, which we can explicitly then replace with by things that are dependent on the shear and on the scalar field and on Vlasov matter. Now, this would be not particularly useful if we can control this by itself, but of course we can. There is, if you look at the Bianchi equations for the Weyl tensor, this gives you a Maxwell type system for these 2 fields, E and B. And this gives you almost closed energy estimates. You just then have to deal with some shear terms, but in particular, which is the main difficulty, because you look at the Bianchi equations of the spacetime metric, there's a spatial derivative in there and a time derivative. This leads you to first order matter terms, both in the scalar field and in the full thing in Vlasov. The way to then regain this is using the momentum constraint. That gives you an elliptic estimate on the shear by looking at both the momentum constraint itself and this conjugate version that you get in the Bell-Robertson variables. This gives you 1 level of regularity back. So you lose 1 when you first introduce these variables, but you gain it back at next order and can then write down a closed estimate for the full thing. I'll say what's on the next slide verbally and then skip past it. Actually, I'll maybe just open it up and then I'll say it. Okay, so for the scalar field, this is, I am putting something that's under the rug here. This is, though, in this result, and to an extent also in the result, the original one, something that is similar to what you can do just in a toroidal case in the original Laniansky Spake paper. This is just quotation marks, wave energy conservation, plus dealing with the fact that you are perturbing near a large normal derivative, where you need to use the Laplace equation to get rid of some large terms efficiently. What you then observe, though, if you look at the evolution equations, is that in all of them, besides the momentum constraint, the scalar field is asymptotically always going to dominate the Vlasov terms. And because of that, for a lot of these energy estimates, because the momentum constraint just ends up not being too relevant because that's poorly behaved towards the past anyhow, we can get close energy estimates for everything if we just assume some weak control on Vlasov matter, slightly oversimplifying. In the two-dimensional case, we can then, because the estimates for the shear are very straightforward, just get almost closed energy estimates for scalar field, the shear, then some curvature terms to deal with some commutation errors, and then sufficiently good black box for Vlasov. In the three-dimensional case, we then need to add in these extra order things, deal with the Bell-Robertson's formalism, and deal with this temporary loss of regularity. I think I even maybe forgot a term here, but morally, it's the same idea. We have an energy formalism for the quiescent system. As long as we get some closed way to estimate Vlasov, we're happy. And we can just plug that black box in. We can then improve the quiescent system first, so we can improve the scalar field in spacetime first, and then put that back into this closed system for Vlasov and improve Vlasov. So what happens for Vlasov? Why do we get this slightly, this very anisotropic behavior towards the past there? I briefly mentioned, because I didn't mention it all so far, we don't really look at the metric at all in this entire commutation method, or only very roughly. We end up then having this closed, once we have all these energy improvements, we then just improve the metric estimates after the fact. Again, because the metric is just going to be the worst behaved thing, we try to avoid it as much as possible. Okay, so what does the Vlasov equation look like? In terms of the terms that mainly interest us, we can split those into the two important ones, which is this first linear horizontal term and this vertical term dependent on the shear. This terminology, horizontal and vertical, goes back to Sasaki because this is something which lives geometrically on a tangent bundle equipped with the Sasaki metric, which is the natural induced metric on the tangent bundle. The vertical derivatives that's just a fancy term for momentum derivatives, and the horizontal ones are these naturally orthogonal spatial derivatives. But it's basically the spatial coordinate derivatives plus some extra bits depending on the momentum. So that is precisely orthogonal with respect to the Sasaki metric. There's also some terms that depend on the lapse, but because the lapse converges nicely towards the path, we don't really need to think about those too much for general idea. First, as to what happens heuristically. Again, the picture we would expect is that this is velocity term dominated. So very heuristically, we would expect the thing that dominates towards the past to be the case where we can ignore the horizontal terms because these are essentially spatial derivatives. And then in particular, and then also we can roughly ignore the lapse terms because in the VTD equations, that's just constant one. So the thing that ends up being the leading term is this shear term here that's scaled by 1 over t. If we then just solve this formally, we get precisely this shape that we have for our asymptotic distribution once we turn around this rescaling, just that instead of our limiting shear, we have, there should be a hat here. Instead of the limiting shear, we have the trace-free part of whatever the shear is in the formal VTD solution. The way one can utilize this, and what then actually happens in the evolved case, is that because of the transport equation, the Vlasov equation, we can, and in some parts do, look at this as a transport system, where the leading evolution of the momentum variables is then given by the shear term, and the leading part of the spatial coordinates is this a to the minus 1 vi over v0. So this here, because this here is never going to, in either spatial dimensions, behave worse than t to the minus 1/2, if we integrate this and have some weak bounds here, our spatial coordinates aren't going to move around too much. We can easily work local coordinates, at least for a bit. And then we just have to concern ourselves with how the momentum behaves. In particular, if we have a nice estimate for the shear, and it turns out, because of the way I talked about earlier as to how the geometric estimate looks for the shear, and the geometric evolution equation looks for the shear, you can get a very sharp estimate for the shear at 0 order. That means you can then, just by integrating this, also control the momentum support, and then in the masses case, the momentum support towards zero. As we approach the Big Bang, as I said before, this is going to degenerate, but this gives us enough of a bound that as long as everything works and all the energy estimates give us, that the energies are then bounded until we reach the Big Bang. This always means we can extend our bootstrap interval, and this gives us enough of what we need for our continuation argument. You can use, or you also just use this characteristic method in and of itself to then control how f behaves, and then with some smaller nuances as to how f compares to the FLRW solution. This ends up not being particularly useful for the energy estimates, though, because the way we then just want to look at the energy estimates in a more natural way is that we get an energy conservation mechanism by just using the fact that the time derivative is this x operator here and then integrating by parts. This gives you already at zero order a more a sufficiently good estimate. The main issue that you encounter is when you commute this at higher orders. Schematically, you want to commute this with both horizontal and vertical derivatives to bound the entire distribution. And this gives you terms of more or less this form here. I'll see if I can schematically go through them. So you have, at first, if you commute this, again, we don't care about the parts that are from the transport operator at the time derivative, this x bold. That's something that is the nice bit that gives us energy conservation. So we just have to control these error terms. The first error term is one where a vertical derivative ends up hitting a momentum variable in this term that behaves like t to the minus 1 times epsilon. That's going to be a borderline term we have to be careful with, but because we have estimates on epsilon, we can control this. That's fine. Then, in general, we're going to have terms where we lose a horizontal derivative, but gain a vertical one. This term here due to commutation errors, and this term over here then just if a spatial derivative falls on sigma in this borderline term. This term here in particular, the one that's dependent on nabla shear, that one is going to be harder to control because we can't control the derivative of the shear as sharply as the shear at zero order. So this here might behave worse than t to the minus 1, and that might break our estimates. On the other hand, we have something where we gain a horizontal derivative but lose a vertical one when from the first linear term that we had earlier. And then there's some other error terms that we don't need to think about too much. What's the idea here, though? The idea is that still the terms that are difficult are the ones where we have more horizontal derivatives. That's the ones that might behave like t to the minus 1 and might break our estimates. Are the ones that have more horizontal derivatives. They enter in linearly in Vlasov. This here is not something that's small as opposed to shear, but it is something that has time integrable factors in front of it. And that ends up giving us a hierarchy. In the case where we start off with just vertical derivatives, all these terms in the second line here, especially these really difficult ones, these don't occur. This one we can control. And if we have some weak control on the case where we have one horizontal derivative, that's enough to integrate this and treat this as an error term. And from there, we can iteratively increase the amount of horizontal derivatives to get a full control at whatever Sobolev order we need. Until we get all the way to the very top, where then this additional term, of course, doesn't occur because we've run out of horizontal derivatives. And then we end up getting a closed estimate for some hierarchical control of these. Yeah, we can use this hierarchical control to get a full bound on the Vlasov distribution at higher orders. Or instead of iteratively improving, we can just use the fact that we have a strict distance to t to the minus 1 in this horizontal term to get a closed estimate for scaled combined energy, where depending on how many horizontal derivatives fall on the Vlasov distribution, we scale this with an additional factor. And this is the Vlasov black box that we can end up just inserting into the quiescent system. We just look at the commuted Vlasov equation for each of these particular combinations of horizontal and vertical derivatives of f minus the reference, and get a closed estimate depending on all the other spacetime variables for this combined quantity. And that will be good enough to get improvements. And once you then get improvements on the spacetime and on the scalar field, we can plug this back into this idea of hierarchical control to iteratively improve each single derivative order with a more sharp thing. Well, this here would then only give us that the Vlasov distribution doesn't diverge worse than some inverse power of A. Cool. Any questions on this bit? Otherwise, I have, it was exactly 5 minutes to deal with the last bit. that was now all on the Vlasov stuff. In the two-dimensional case, there is a corollary you can obtain where we pretend that the Vlasov wasn't there at all, because to an extent for the asymptotics we just look at the Einstein scalar field system in 2+1 dimensions. This gives you another corollary, which is about behavior of vacuum solutions in U1 symmetry. The result that is already known beforehand is that in the Philadelphia spec paper for subcritical generalized Kästner solutions that I mentioned earlier, there's also a statement on stability in polarized U1 symmetry, a particular symmetry class that I, for the sake of simplicity, won't define, where you also have stability to vacuum solutions in the symmetry class if you move towards the past. You can prove this there almost just along the way for the general idea. The idea in both proofs is that you have to control components of a particular frame that you transport along the evolution. And in this particular frame, in the case where there is a scalar field, you can show that if you are subcritical, then these critical terms, gamma 1, 2, 3, they don't behave too badly. Yes, in this dimension. They aren't, but you can integrate this near diagonal system, and it gives you good enough behavior that you can deduce everything else you need from there. In the polarized U1 symmetric case, this is just identically vanishing. This is just 0, and that way it's even simpler to show that you have stability in the vacuum case. This also goes all the way back to the BKL conjecture, where they also essentially phrased it very, very originally as you have to satisfy something that is for the frame that is satisfied in polarized U1 symmetry on the torus, to avoid bad terms entering into a heuristic ansatz that depend on having a negative Kästner exponent. And in the case where it just vanishes, then these terms can't occur and everything's fine. What you then get is that this is also not dependent on geometry to an extent. In the original result, this is on the torus, and you don't really care in which direction you require symmetry. It can be in the direction of the negative exponent. It can be in that one of the positive one. It's always going to be stable. For us, we look at polarized U1 symmetric solutions where the quotient, once you divide by an S1, you have your time interval times a closed orientable surface. And we look at solutions that actually have a Big Bang singularity, so we exclude the 0, 0, 1 Kästner exponent solution. In that symmetry class, we can show that that's partially true and extendable, and that while we don't get stable blurb for the Kretschmann scalar itself, we get stable blurb for a renormalized analog of the Kretschmann scalar. The idea, and the reason I mentioned this, is that you can actually pull up 2+1 results all the way up directly to the 3+1 system. And the idea goes back to Moncrief, where you can just write down this conformal splitting of metrics if you have polarized U1 symmetry into this bit, which is a direction of symmetry, scaled by an exponential of a scalar field phi, and then this conformally renormalized rest of the spacetime metric, which is a 2+1 metric. This metric G bar then just satisfies the Einstein scalar field equations with respect to this scalar field phi up here. And then what I then do in this paper is just, at the moment where we have our stability results in 2+1 dimensions, we can then just pull this up directly back to the 3+1 system. Because the 2+1 result works in CMC TC gauge, and as I mentioned before, we kind of need this, or at least I wasn't able to fully use the Teichmuller structure that you would want to use in 2+1 gravity, which is a bit more a rigid phase space, which I'm not going to introduce here, but it allows you to usually get easier control on the asymptotics of the solutions to the Einstein equations in 2+1 dimensions, but that requires you to have a non-trivial shear, which is difficult to control. Whilst in CMC-TC gauge, we don't have this dynamical phase space picture, but we are able to ignore the shear and are thus able to get to this result in stability 2+1. But the issue is that when you translate this back up, while the foliation is CMC in the 2+1 sense, it's not CMC in the 3+1 sense, which is precisely what leads you then to have to consider these renormalized quantities for the Kretschmann scalar and for the shear, for the mean co-algebra blow-up, and also for all other quantities. But essentially, if you do these correct renormalizations depending on this, what is ultimately this conformal factor, then you can get stable blow-up and also convergence results for all the space-time variables that are relevant. And you can, at least, for the second fundamental form, you can do this, and for the Kretschmann scalar, and then, for the metric components that you can control of the scalar field, kind of trivially. what one can hope from this is that given how nice the analysis, even in presence of other matter models was in 2+1 dimensions, that if one is careful, one can maybe translate Einstein equations in presence of matter, be it Vlasov, be it subcritical fluids, maybe that on a 3+1 solution with polarized U1 symmetry, translate that down to a 2+1 system, solve that there with a suitable black box for this additional matter model, translate that back up, and then get stability for Einstein matter solutions in the symmetry class in the same way that you can get this for vacuum. But also just in and of itself, it extends the results both for Lotniansky and spec to these more general spatial topologies where M is not just a torus, but also a two-sphere or a closed two-surface. A closed hyperbolic two-surface, and thus all closed two-surfaces, I guess. Yeah, that was all I had. I think I am at my time anyhow. So yeah, thanks for listening, and I'm open to questions.
Thanks, Liam. Thanks, Liam, for the wonderful talk. So if anybody has any questions from the audience, please go ahead and unmute yourself. Do you have any questions from the audience? Okay, I guess nobody has any question. I'll go ahead and ask some questions, Liam, if that's all right.
Yeah, of course.
Yeah, so can you like explain the last part a bit, like the E1 polarized part? I'm actually quite interested in that. I wanna.
Yeah.
Yeah.
Yeah. Okay. So it is really just this conformal idea here. For polarized U1 metrics of the particular type that we look at, we can, okay, so that regardless of that, just polarized U1 symmetric metrics, we can split this up, going back to us up a Moncrief. You can probably even, if you want to look at something a bit more complicated, then you won't have stability. But what you can look at beyond that is that you can even look at just U1 symmetry without polarization. That will just give you that you couple to a wave map, and that will probably lead to instabilities. Wild conjectures from my end, that's how that works, but that is at least what happens in this formalism of Moncrief. But as is, this is just something that nicely pops out of U1 symmetry, and you can translate this down to a 2+1 system. The types of solutions that you look at here are the ones, and that also tying back to the BKL conjecture, in direction of the symmetry. This Kästner exponent, basically Kästner exponent, is the direction, is the one with that is negative for the vacuum solution, which is the way that you can have stability. That's precisely the requirement that you heuristically expect from BKL. And at the moment where this symmetry requirement cancels out the bad term that you would get from the frame, this gamma 1 to 3 term in front of Lotniansky and spec. And at the moment where that term is cancelled, you can heuristically expect stability. And that is essentially what we prove. Going down to a 2+1 level, then once you have this conformal idea, that is really just, as I mentioned earlier, if we go all the way back. Again, maybe you can make Teichmuller theory work here. Maybe there is a way to deal with the fact that the metric doesn't behave well in presence of a scalar field towards the past. Maybe that's possible. But as is, it is really just the idea that on the 2+1 level, we may need to control the shear and then the scalar field, but that's somewhat similar. We need to be able to control the shear to get control in our quiescent system. And in the energy estimates, these two things just are orthogonal to each other. That the fact that it is written this way is basically just whatever is in the rigid tensor here has to be cancelled out by some pure trace parts over here that we just can't identify with our naked eyes. And because of that, you then get closed energy estimates for the shear, the scalar field, and the lapse, plus some geometric error terms that we don't care about too much. And moment where you then have this way of dealing with 2+1 geometry, which is essentially a simplified idea of how you treat the stability proofs in general, then you just can translate it back up. So it is really, and that's the way how I actually came to it. And also like that would hint me towards this was, it is just we looked at the 2+1 system first because we originally wanted to see whether Teichmüller theory gives us something. Turned out it didn't, but there is this other proof that's just a lot simpler than the other situations. And this then just constantly gives you this thing back, just if you translate the literal FLRW setup back up. You could probably, if you get the right formalism in 2+1 gravity for the torus case, you can probably even fully reproduce the types of results that are in for the Vlasov spec for the full range of Carlson experiments. They just would have to adapt the 2+1 formalism in the correct way. But yeah, this covers the ones where you don't have the torus as your spatial two surface.
I see. Yeah, thanks, Liam. Thanks. Yeah, one more question is like,
Mhm.
so once you go down, do everything in 2+1 level,
Mhm.
2+1 gravity coupled to like wave maps or whatever, and that's 2+1 in the 2+1 setting is a CMC. The slicing is
Yes.
CMC, but if you lift it up for the 3+1, it's not. But
Yeah.
does it matter? I mean, it doesn't matter, right? It shouldn't
It,
matter, right?
it doesn't matter for the evolution. Like the solution you get, you just formally translate up, and that is fine. You can just write
Right.
down what it is. The unfortunate thing is then just that because it is not CMC, and because it's not CMC, the synchronization is slightly off. The reason all of these Big Bang stability results, like if you just want stability of the Kretschmer scalar itself, the reason that this is all nice is that it's sharply synchronized. It ends up being synchronized in this case as well, just because it's basically given by level sets of phi, or level sets of level sets of phi. But we are approaching it slightly off kilter, and this approachment off kilter is just something you have to account for this renormalized Kretschmer scalar. This is just you end up being able to control all of your variables, just you aren't able to control in this foliation the natural variables because it is in a certain sense not the natural foliation that you would want to look at. It is the foliation that you end up inducing by this conformal formalism and not the one that is most suited to synchronize the Big Bang formation. But yeah, this is basically morally you get the same thing. You just have this exponential factor in here that is different to what's in the other results, but you can still get almost strict estimates on the blow-up rates for the Kretschmer scalar itself because you can control phi.
Right. Yes. Thanks so much, Liam. Yeah, that explains it.
Hmm.
Thanks so much. Anybody else has any questions from the audience? If you do have any questions, please unmute yourself. But I guess if there's no more questions, then we'll just stop.